Assalamualaikum and good morning, everyone.
Waalaikumsalam Nada.
Okay, so today we are going to learn about stress. Okay, not the stress that you are experiencing right now. It's the stress on the solid. Okay, on the solid. So from uh, from since midterm, we have learned about the deformation. Okay, so the deformation and how to measure the strain after the solid is deformed. So when the solid is deformed, then there will be some sort of stress um, experienced by the solid after its deformation. So I think you have learned some of the stress concept from subject like solid mechanics or strength of materials. But for today, we are going to look at how we can incorporate the things that we have learned so far, which is the deformation, and how we can use the deformation into calculating the stress. So at the end of this lecture, you will be able to understand and calculate the stress tensor and then determine the principal stress and strain. Sorry, actually principal stress and the plane. Okay? And then determine the other stress tensor definitions. So I think you have learned from subject SOM and solid mechanics about stress tensor and also principal stress. Probably you have learned about Mohr circle. So in Mohr circle, you can calculate principal stress. So here we are going to look at how we can calculate principal stress from stress tensor. So we have learned about the kinematics aspect of the motion and deformation of a continuum body. And motion and deformation give rise to interactions between the material and neighboring material in the body. So each particle will experience different deformation depending on its interaction with its neighbor. So the results of the interaction is the stress, which is responsible for the deformation of the material. So before we can go into learning more about the stress tensor, let's look at the stress vector or the traction vector. So the traction vector is equal to the resultant force acting on a surface divided by the surface area over which it acts. Okay, so it's like force over area. So force over area, we get the stress or pressure. So here we have force F acting on an area A. Okay, so we pull this bar from both sides or from both ends, and we can calculate the stress or the pressure. If we apply an external force to an object, it responds through the combination of acceleration and deformation. So when we pull, the bar can either elongate or break and so on. So each particles in the bar will respond according to its own strength, okay, in the form of acceleration and also deformation. So the object remains cohesive. Cohesive means intact as the atoms of the material interact with one another, resulting in an internal force distribution to balance the external force. So if you look at the last figure here, so there will be some force distribution between the two bars here. So each of the particles will have um, its own force. Okay, so the force is distributed um, accordingly on the surface area. So consider a body shown here. So body at the reference configuration. So we let's say we have applied a force somewhere in the middle of the body. So the force on a small element, okay, let's say a small surface, we call it dA big X, and the force is dF big X. And then an X here is the normal of the surface. So imagine we make a cut through the body to expose the internal surface. There are internal forces acting on the surface in the current configuration that keeps the object in one piece. So let's say if you apply some sort of deformation into the body, then on current configuration, at the same surface, now in the current configuration, let's say the area is dA small x, so different area but the same particle, okay, and different force dF small x, and different normal. So let's say it's changed in position and changed in location as well. So in the current configuration, so figure B, the instantaneous force dFx small x acting on a small area dA small x. So meanwhile, in the reference configuration, the force is dF big X acting on a small area dA big X. Okay, so similar to like what we have learned in deformation. So small x represent current configuration, big X represent the reference configuration. So now here we have two different force and two different surface area on the same particle. So what this slide is showing is that when the particle is changed in position or got deformed, then the surface area might change and the amount of force on that surface also change. Okay. So because of there are two kinds of force and area after deformation, then we can define different kinds of stress depending on which force and which area that we are going to use. So the first traction vector is known as the Cauchy traction vector. So we define it as a T small x. So it is the true traction vector or true stress. Okay? Is defined as the instantaneous force in current configuration per unit surface area in current configuration. So it's basically dF small x over dA small x. And then we have the second definition of traction. We call it the first Piola-Kirchhoff traction vector. So it is written as T big X, or the nominal traction vector or nominal stress is defined as the instantaneous force in current configuration per surface area in reference configuration. So it's dF small x over dA big X. And then lastly, we have the second Piola-Kirchhoff traction vector, which we write as T big X star, defined as the force in the reference configuration over surface area in reference configuration. So it's dF big X over dA big X. So if you still remember in SOM, you have learned about true stress, nominal stress. So that's basically the different stress measured over which area you are going to use. So sometimes if you divide with original area, then it's a maybe nominal stress. If you divide by the current area of the material, it's the Cauchy stress. Okay, so there are two or three different kind of stress definition depending on which area you are dividing the force. Okay. So we focus on the Cauchy stress tensor because the Cauchy stress tensor is basically what we are using a lot in, let's say, finite element software or in experiment, while the other uh, uh, traction or stress is just calculated stress that you cannot measure. So Cauchy stress tensor, we use the symbol sigma, is defined as tau x equals sigma dot n. So n is the normal vector of the surface area, or it's equals to n dot sigma transpose. Okay, so there are two formula, but using the same stress. Okay, but this depends on the position which uh, which place you put the sigma. Okay, either before n or after n. So the traction vector is not in the direction of n. It can be represented as the sum of the vectors along and perpendicular to n. So Tx is basically Tx dot n plus n cross Tx cross n. Okay, so basically the stress traction Tx, there are two components. There is one perpendicular component and the other is parallel component to the surface. So we have Txn. Txn is the stress traction vector normal to the surface, and Txs is the traction vector parallel to the surface. Okay, so the formula is here. So let's look at an example how to calculate the traction vector. So let's say you are given the stress tensor sigma and the unit normal vector to a surface. So let's say this is the stress tensor and this is the normal vector to the surface. So determine the Cauchy traction vector and then determine the normal and shear component of the Cauchy traction vectors. So the Cauchy traction vector, you just use Tx equals sigma dot n. So this is the sigma, the big matrix here. And then dot, you just multiply this tensor with the vector. So you just multiply as usual, you get this value. So this is the Cauchy traction vector. And then the question asks you to find the normal component of Tx. So you just calculate Tx dot n times n. So this is Tx just now, dot n. So you have to use the dot product concept. Just multiply 1600 times 1 plus 400 times 2 plus 100 times 2. And then times the normal vector. So 1 over 27 is basically the perkali here, the coefficient here, 1 over 3. There are three things here, so 1 over 3 kuasa 3, okay? And then when you calculate, you get this answer. And then lastly, the shear component, you just minus the Cauchy traction minus the normal component, okay? Tx minus Txn. So you get the shear traction. Okay, so it's kind of straightforward. Okay, kalau soalan final pun macam ni je lah. Okay. Okay, so I leave this exercise to you to try later, maybe by yourself. Okay, so the calculation is straightforward. You just follow this example. Okay, if you are stuck anywhere, just WhatsApp me. Okay. Okay, now we have learned about the Cauchy stress tensor, and now we look at how to determine the principal stresses and the principal planes of the stress tensor. So we know that the Cauchy stress tensor, sigma is the second order tensor or 3 by 3 matrix. So here we know that a 3 by 3 matrix will have its own eigenvalues and eigenvectors. So the eigenvalues of the stress tensor are the principal stresses, sigma 1, sigma 2, and sigma 3. And the eigenvectors are the principal planes. Principal planes or the normal vectors of the principal stress, M1, M2, and M3. So to determine the principal stresses and planes for the stress tensor or the Cauchy stress tensor, you need to find eigenvalues and eigenvectors. So we have learned about this. So it's just uh, a revision back on how to determine eigenvalues and eigenvectors. To find the principal stresses and plane of this Cauchy stress tensor. So firstly, you can find the determinant sigma minus lambda I, and then you get this equation and equal it 0, and then solve for lambda. So when you solve for lambda, you get three values of lambda. One is 15, another one is 6, and the other one is negative 15. So megapascal here is actually the unit for the stress. Okay? Sometimes it is given to you. So if it's not given to you, then you assume it's no unit lah. Okay, but it's actually megapascal given. Okay, so if it's not given to you, then you assume it as no unit. So now you have three principal stress: sigma 1, sigma 2, and sigma 3. You can find through finding the eigenvalues. And then after that, you can find the principal plane by calculating the eigenvectors. Okay, so this is the way to calculate the eigenvectors. So you get first plane is this one, 3e1 plus e2. And then the second plane is n2 equals e3. And then the third one is n3 is e1 minus 3e2. Okay, so you can try later on finding these eigenvalues. Okay, so it's similar like we have learned last time. And then this picture just showing what is the meaning of principal stress and principal planes. So here is the regular box that consists of the Cauchy stress tensor. So you can assume that this box is a small element in the body. So a very small element in the body that produce the nine component of this Cauchy stress. So here the middle, the diagonal values here represent the normal stresses, while the non-diagonals are the shear stress. So here if you look at this arrow yang keluar dari surface here, like this arrow yang menegak here, sigma 22, and then the arrow here, sigma 33, and this arrow here, sigma 11, has the value 12, negative 12, and 6. So this value represent the normal stress. Okay, normal stress taken from these diagonal values. And then the other stresses like sigma 12, sigma 21, sigma 23, sigma 32, and so on are the shear stresses. Okay, so shear stresses they are acting on the surface or parallel to the surface, while the normal stresses acting perpendicular to the surface. So the meaning of this principal stress is that if you rotate this body here, when you rotate this body at the right angle, then you will find that at certain angle, there exists only three stress value, which is 15 megapascal, 6 megapascal, and negative 15 megapascal, while the shear stresses are now become 0. So at this angle, actually the cube only showing the principal stresses. Okay, the principal stresses actually represent the normal stresses at the point where there are no shear stress. Okay, So it's the matter of at which angle you look at the point in the material to produce the principal stresses. Okay, and then from the principal stresses and principal planes, we can calculate the maximum shear stress produced on that specific point. So the shear stresses on the principal planes are zero. As I said earlier, if you rotate the cube at the right angle, then you will only get the cube with principal stresses, while the shear stresses are equal zero. Okay, because we know that the principal stress represent a diagonal tensor. So the maximum shear stress can be determined from these principal stresses. And the derivation is not shown here. So the maximum shear stress is determined by this formula. So T max or tau max equals 1/2 of the maximum value of the principal stress minus the minimum value of the principal stress. So here sigma max is the maximum principal stress and sigma min is the minimum principal stress. Okay, so the plane of the maximum shear stress lies between the plane of maximum and minimum principal stress. Okay, so let's look at an example how to determine the maximum shear stress. So from the same example as example number 2, determine the maximum shear stress and its plane. So from example number 2, we already calculated the principal stresses minus 15, 6, and 15. So the maximum shear stress is just 1/2 of maximum minus minimum. So the maximum is 15 and the minimum is negative 15. So 15 minus negative 15 divided by 2, you get 15 megapascal. So 15 megapascal is the maximum shear stress that that point can achieve. Okay. So the plane of the maximum shear stress or principal stress you have calculated earlier, and then you can calculate the maximum shear stress. The plane of the maximum shear stress is just taken the uh, plane of the minimum stress minus plane of the maximum stress or the principal plane, and you calculate, you get this plane here. So here the figure, the first figure here is the 9 component of stress, and then the second figure here when you rotate the cube at the right angle to get only the principal stresses, and then when you rotate at the right another correct angle again, you will get the maximum shear stresses. So the maximum shear stress is 15 megapascal, while so we don't know at this point what is the stress, the other stress component. So we know that at this point here, it achieved the maximum shear stress. So here it shows an example how to calculate the angle here. So if this question come out in exam, you will be required to calculate the principal stresses and the maximum shear stress only, while the other things like drawing this thing, tak tanya lah, okay? Like finding this angle, not going to be asked to you. Okay? You will be asked to calculate the principal stress and the maximum shear stress. And again, this is an exercise for you. So you can try calculate the principal stress and principal plane using the concept of eigenvalues and eigenvectors. So if you look at this stress tensor, so it has all components in the stress tensor has values. So when you get this kind of tensor, then you will realize that to calculate the eigenvectors later will be slightly difficult compared to only having this kind of stress tensor. So when you have more zero in the stress tensor, to calculate the eigenvectors is a lot easier compared to having this. So you can try calculate the principal stress and planes using symbol lab or MATLAB, okay? And then determine the maximum shear stress using the formula just now. Okay, so that's about the Cauchy stress tensor and the principal stress and principal planes. So we have learned previously that there are different stress definition, which is the first polar Kirchhoff traction and the second polar Kirchhoff traction vector. So this vector is defined depending on the surface area that you use. So when you use different surface area and different force, and of course there will be different stress measure as well. So we have learned about Cauchy stress tensor. So in this slide, we are going to look at the different stress measures other than the Cauchy stress tensor. So Cauchy stress tensor is the most natural and physical measure of the state stress at a point in the deformed configuration, and it is measured per unit area of the deformed configuration. So the Cauchy stress tensor is depends on the deformed configuration. So Cauchy stress is commonly used in spatial description problems such as in fluid mechanics. So in fluid mechanics, like in CFD, also have particles in the fluid also have stresses in between them. So in fluid mechanics, they use Cauchy stress to define the stress in between different particles. However, in solid mechanics, because we can define uh, the particles movement based on different configuration like reference or deformed configuration. So in solid mechanics, the Lagrangian description is commonly used, or the reference configuration. So the stress measure must be expressed in reference configuration. So because of that, we need to define different stress measure that is only mathematical, that cannot be measured in experiment, but this stress tensors or the other stress measure is only be used to facilitate the analysis of stress in a solid body. So the first stress tensor is known as the first polar. Here, so the first figure is undeformed body, and the second is the deformed body. So we use big letters to represent undeformed body and small letters to represent deformed body. So basically, it is the stress that depends on the deformed body. Undeformed body. Okay. So this T big T here, or the T big X here, is the first polar Kirchhoff traction vector. So if you want to find the the stress depending on the first polar Kirchhoff traction vector, so we can use this formula: T big X equals P dot big N. So P here is the first polar Kirchhoff stress tensor, and N is the normal to the area dA. So P depends on the area of the body or of the small particle at the undeformed configuration. But Cauchy stress tensor is depends on this dA, or the area on the deformed body. So for the first polar Kirchhoff stress tensor, it depends on the area on the undeformed body. Okay, so by derivation, using Nonsense formula. So we have learned Nonsense formula back in lecture number 3A, but we didn't use this formula. So after applying this formula, we know that P, or the first Euler-Kirchhoff stress tensor, equals J times sigma times F inverse transpose. So J here is the Jacobian of F, and then sigma is the Cauchy stress tensor, and F is the deformation gradient, and negative T is this inverse and transpose. So from this definition, we know we can describe that P is a two-point tensor, okay, similar to F, similar to deformation gradient, because P relates the point in the undeformed configuration to its corresponding deformed configuration. So P depends on the force on the deformed configuration divided by the area on the undeformed configuration. So by derivation, again, P is unsymmetric tensor. So when you calculate P later on, you must make sure that P you calculate will get unsymmetric tensor. Okay. So that's P, the first Euler-Kirchhoff stress tensor. So we have the second Euler-Kirchhoff stress tensor. So the second Euler-Kirchhoff stress tensor basically relate the force in the undeformed area or undeformed body to the force in the undeformed configuration. So this is just definition derivation. So to calculate the second Euler-Kirchhoff stress tensor S is using this formula. So F inverse times P, or equals J times F inverse times sigma times F inverse transpose. So S, the second Euler-Kirchhoff stress tensor, is symmetric. Okay, it's always symmetric, while P is unsymmetric. Okay, so let's look at an example on how to calculate the first and second Euler-Kirchhoff stress tensor. So you must make sure that to calculate first and second Euler-Kirchhoff stress tensor, you must find the deformation gradient first. Okay. So here in this question, you are given the deformation gradient. So let's say if you are not given deformation gradient, so you need to find deformation gradient first, F. So F here is this tensor, and then this is the Cauchy stress tensor. So if you are not given Cauchy stress tensor, then you need to calculate. Okay, so usually you are given sigma, but you are not given deformation gradient. So you need to calculate deformation gradient. Okay. So firstly, you need to determine the Jacobian. So just determinant of F. And then after determining the Jacobian, you need to inverse the deformation gradient. And then after inverse, you transpose. And then after you calculate this thing, J, F inverse, and F inverse transpose, then you can calculate first Euler-Kirchhoff stress. Okay, so P equals J sigma F inverse transpose. Then you calculate as usual. Okay, so calculate slowly lah. Okay, sebab ni tak ada nombor. So you end up with this tensor. So if you look at this tensor, it is not symmetric. Okay, because you have the C sine A term here that causes the tensor not symmetric. So P is always not symmetric. Okay. And then after you calculate P, you can calculate the second Euler-Kirchhoff stress tensor. So S is just F inverse times P. Okay, so you calculate this tensor. So calculate slowly, you get this answer C over B. The other are zeros. So here you know that S is symmetric. Okay, so if you get S not symmetric, then kira lain sekali lah, maksudnya salah kira. So always remember, S is symmetric and P is not symmetric. And Cauchy stress tensor is also symmetric. So Cauchy and second polar Kirchhoff is symmetric, while first polar Kirchhoff is not symmetric. Okay, so later on, maybe in next week lecture or the following week, we are going to look at how we can use the first and second polar Kirchhoff stress tensor. Okay, so this is an exercise for you. So here in this question, you are not given deformation gradient, but instead you are given deformation map. So from here you need to determine the deformation gradient. Okay, so nanti silap sikit sini. So ni actually plus. Okay, so you need to determine the deformation gradient. So I think deformation gradient you can determine by finding this the differentiation of this. So you get A 0, 0. Okay, so I think this is the deformation gradient. Then from here you can calculate the F inverse J and F inverse transpose. Then from here you can calculate P equals J apa tadi sigma something sigma FE, and then S equals F inverse P. Okay, so kind of straightforward. Okay, so kalau dalam final pun soalan dia straightforward macam ni je. So mungkin akan buat salah kira macam midterm hari tu lah, tiba-tiba A jadi 1, C jadi 2, tak tahu mana datang. So please make sure you calculate correctly. Okay, don't simply put numbers. You are not given any numbers. Okay, sometimes you are given numbers, sometimes not. Okay. Okay, so that's it for today's lecture. So we have covered the deformation and stress. So after this, we are going to look at the stress or the balance equation. How we can determine the balance of let's say volume or the velocity of the particles in the body, so that we can further calculate the motion, okay, the motion of the body. And then the following week, maybe we are going to look at the different material properties of a solid. Okay, we have linear properties and we have also non-linear properties, and how we can use these different properties to determine the stress and strain of a body. Okay, and then maybe in week 13 or 14, I will set up a talk from two different researchers that use continuum mechanics, and maybe you can learn something from them. Okay, and not to forget, I already uploaded in Kalam your assignment. Okay, so assignment this semester, I don't have enough time to make an assignment using MATLAB using software so I put an assignment that basically requires you to calculate maybe using Symbolab or using manual calculation. Okay, so try to do that assignment and try to discuss among you guys. And maybe some of the question in the assignment will come up in final exam. So try to do it, try to understand the assignment. So the assignment is 10%. And the due date is week 14, okay, end of week 14. So you have about 5 weeks from now to do the assignment. Okay, so that's it for today's class, and hope to see you again next Thursday, inshallah. Assalamualaikum and goodbye.